Welcome back to another episode of Data Deep Dive, where we explore the intricate world of databases and data management. Today, we're going to dive into a critical aspect of distributed databases, partitioning. We'll unpack how partitioning works, the challenges it presents, and the various strategies for managing it effectively. So grab your headphones and let's get started. To kick things off, let's clarify what we mean by partitioning. In the realm of distributed databases, partitioning is essentially the process of splitting data across multiple nodes. This becomes crucial when dealing with large datasets that simply can't fit on a single machine. One popular method used for this is consistent hashing, which aims to distribute data evenly across nodes. However, it's worth noting that this method can sometimes lead to unfair splits, particularly when new nodes are added to the system. Take Cassandra, for example. This well-known distributed database operates with a default of 256 partitions per node. When a new node joins the cluster, it takes ownership of half of the partitions from the existing nodes. While this randomization can create uneven loads at first, over time it tends to average out, leading to a more balanced distribution of requests. With the release of Cassandra 3.0, a new rebalancing algorithm was introduced to tackle these unfair splits more effectively. Speaking of rebalancing, let's delve into how it works. There's a spectrum here, ranging from fully automatic rebalancing, where the system autonomously moves partitions between nodes, to fully manual rebalancing, which requires an administrator to step in and make changes. For instance, systems like Couchbase and Riak can suggest partition assignments automatically, but they still need human approval before those changes are implemented. However, rebalancing is not without its challenges. It can be an expensive operation that involves rerouting requests and moving data around, which can overload the network and degrade performance if not managed properly. This issue is particularly concerning when combined with automatic failure detection. If a node becomes overloaded and is mistakenly identified as dead, the system might attempt to redistribute the load, which could worsen the situation and potentially lead to a cascading failure. This highlights the importance of having a human in the loop during rebalancing. While automation can speed up processes, having someone oversee operations can prevent unexpected issues, ensuring the system remains stable. Now let's tackle a crucial question. How do clients know which node to connect to when making requests? As partitions are rebalanced, the mapping of those partitions to nodes changes. This is where service discovery comes into play, which is a broader issue affecting any network-accessible software that aims for high availability. There are several approaches to service discovery. One method allows clients to contact any node directly. If that node doesn't own the requested partition, it simply forwards the request to the correct node. Another approach involves a dedicated routing tier that determines where requests should go, acting like a partition-aware load balancer. A third method requires clients to have knowledge of the partition assignments, enabling them to connect directly to the appropriate node. However, keeping track of these changes in partition assignments can get quite complex. Many distributed systems rely on coordination services like Zookeeper to manage this metadata. Each node registers with Zookeeper, which maintains the authoritative mapping of partitions to nodes. When changes occur, like a node being added or removed, Zookeeper notifies the routing tier, ensuring that routing information stays up to date. For instance, LinkedIn's Espresso database uses a system called Helix, which depends on Zookeeper for cluster management. Other systems, such as HBase and Kafka, also utilize Zookeeper for tracking partition assignments. Interestingly, Couchbase takes a different route by configuring a routing tier called Moxie, which learns about routing changes directly from the cluster nodes. Now that we've covered the basics of partitioning and service discovery, let's shift gears and talk about query execution. Most NoSQL databases support straightforward queries that read or write a single key. In contrast, massively parallel processing, or MPP, relational databases, often used for analytics, support much more complex queries that involve joins, filtering, and aggregations. In these MPP systems, the query optimizer breaks down complex queries into execution stages that can run in parallel across different nodes. This parallel execution is particularly beneficial for queries that need to scan large datasets, making analytics more efficient. As we consider the importance of analytics in today's data-driven world, it's clear that there's significant commercial interest in optimizing these processes. We'll explore techniques for parallel query execution in future episodes, but for now, it's essential to recognize that partitioning is a foundational concept that enables scalability and performance in distributed databases. Another vital aspect of partitioning is the need to avoid hotspots, nodes that experience disproportionately high loads. This requires careful selection of partitioning schemes and ongoing rebalancing as nodes are added or removed from the cluster. When it comes to partitioning methods, there are two primary approaches: key range partitioning and hash partitioning. Key range partitioning organizes keys in a sorted order, allowing for efficient range queries but risking hotspots if keys are frequently accessed in close proximity. On the other hand, hash partitioning applies a hash function to keys, distributing the load more evenly but sacrificing the ability to perform efficient range queries. Dynamic partitioning is another option, offering more flexibility in assigning partitions to nodes and enabling the movement of partitions as needed. This adaptability is crucial for maintaining performance and availability as data and workloads evolve. We also touched on the interaction between partitioning and secondary indexes. Secondary indexes need to be partitioned as well, and there are two common methods: document partitioned indexes and term partitioned indexes. Document partitioned indexes store secondary indexes in the same partition as the primary key, which simplifies updates but complicates reads. In contrast, term partitioned indexes are stored separately, allowing for more efficient reads but requiring multiple partitions to be updated on writes. As we wrap up our discussion, it's essential to recognize that while partitioning enables scalability, it also introduces complexity. Operations that involve writing to multiple partitions can be challenging, especially when considering the potential for partial failures. This is where transactions come into play, allowing applications to group reads and writes into a single logical unit. If a transaction fails, the application can retry without worrying about inconsistent states. In conclusion, partitioning is a fundamental concept in distributed databases that allows for scalability and efficient data management. However, it comes with its own set of challenges, from rebalancing and service discovery to query execution and fault tolerance. As we continue to explore the world of databases, understanding these concepts will help us build more robust and efficient systems. Thanks for tuning in to this episode of Data Deep Dive. We hope you found this discussion insightful and look forward to diving deeper into these topics in future episodes.